Welcome back to week 12 of Bio 6612. In today's lecture, we're going to talk about GE examples for continuous data. So we'll cover GEs and R for continuous data, both implementation and interpretation in this lecture. There are several packages for implementing marginal models or GEs in R. I just have a couple ones mentioned here. This is the sort of original one. It provides basic functionality for fitting GEs. I'm going to mostly work with GPack examples. I like this one because it has a couple added features plus more inference that goes with it. And then this third package, G, is a newer and faster implementation with some features that Professor Alex Kaiser really likes, so that he recommends that one. So the example that we're going to go with for continuous data is this pig weights 2.0 data set. I'm calling it pig weights 2.0 because it's measurements of weights of pigs over time plus more covariates, but it's actually a different study from the other pig weights data set. And in this study, we're looking at how vitamin E and copper level in the feeds of pigs affect their weights. The pigs were weighed weekly for 12 weeks and dosed with varying levels of vitamin E or copper in their feed. There are 3 possible doses of each of vitamin E and copper. And the variables in the data set are weight, which is the outcome, time, which is the week of measurement, pig, which is the pig identifier, this EVIT variable, which is the dose of vitamin E, that's a 3-level categorical variable, and CU, which is the dose of copper, which is also a 3-level categorical variable. To access this data, we're going to install and load the GPack library, and then load the diet docs data. So anytime I load a new data set, I would like to do EDA, and this is especially important for longitudinal data analysis and GEs because you have to figure out how to structure your model. So what I've made here are some spaghetti plots of the pig weights over time at the different vitamin E doses. And it seems like the relationship is relatively linear. There's definitely correlation within pig over time, a strong correlation. And the dose doesn't appear to vary all that much by a dose of vitamin E. The relationship doesn't. Here's that plot. I looked at the same plot for copper, and there doesn't seem to be a strong relationship between copper and pig weight over time, at least visually. So the second part of EDA that I'm going to talk about is looking at the correlation structure. So here I made correlation plots at all of the time points. Actually, there are 12 weeks in this data set. I'm only looking up until week 10 here because it's just fits better on the screen, but normally I would look at all 12. And here you can see in the residuals, there's a strong correlation in the residuals at each of these time points. And you can see that reflected in the actual numbers as well. And along the off diagonal gives you the sort of 1-week correlations, and those are quite strong and quite similar. It does appear that the correlation is larger for time points closer together than time points farther apart. You can see it's decreasing over time. And that seems to be relatively consistently true, that the correlation is decreasing over time, which to me is an indication that an AR1 correlation structure, an autoregressive correlation structure might be appropriate here. And that's what I'm looking for when I look at these plots, what kind of correlation structure might be appropriate. However, it might not be a perfect fit because you can see that the correlation does remain pretty high at all time points, and at some time points the correlation is actually larger, like say comparing week 1 to week 8 is larger than it is comparing week 1 to week 7 or week 1 to week 6. So it's really not a structure. The correlations aren't completely decreasing over time. They just tend to be. So yeah, correlation, but examining that correlation structure and talking about that a little bit more, we'd say that correlation is similar across equally spaced time points. And it's smaller for time points that are further apart. So I'm going to run a couple models here, a couple GE models with different working correlation structures. And the first correlation structure I'm going to choose is the independence working correlation. And that's usually a good thing to start with, because it doesn't you don't have to estimate any correlation parameters. This just assumes that all the observations are independent. And because we have the robust standard errors produced by the sandwich estimator, even the independence working correlation should give reasonable estimates if you have well-balanced data. So below, I'm going to run a GE model with pig weight as the outcome, and time, copper dose, vitamin E dose as the main effects. So first, and the working correlation structure, the independence working correlation structure, is assuming that all observations are independent. So the GPAC library is the one I'm using to run the GEE model here. I'm defining the GE independent model. This GEE GLM model is the main function that we're using to run the GEE, and it has syntax that's very similar to the just regular GLM function, where first I define my formula with weight against the main effects time, EVIT, and CU. I have to designate the ID, which is pig, the identifier that marks repeated observations, the name of the data. I choose a family in the same way that I would for just the GLM function, in this case, continuous data, so I'm choosing Gaussian. And I choose a correlation structure. That's where things get different. And in this case, I'm choosing an independence correlation structure. So just looking at some of the results that are output here. The summary looks a lot like we would see in a GLM model, where you get coefficients, you get estimates, standard errors, and these are the robust standard errors that come from the sandwich estimator. And you're getting some p-values. In this case, the only thing that we see as significant is that relationship over time. None of the levels of the doses of vitamin E or copper are significant here. So I'm also going to run the same model, but with a different working correlation structure. Instead, I'm going to change exchangeable working correlation. And with exchangeable working correlation, you estimate one correlation coefficient, and that would be the same correlation between any two time points in the data. And the only thing that's changing about my code here is this last argument, the core structure equals exchangeable argument. And I'm not going to print out the summary, but we'll look at the coefficients and compare them with the other models in a few slides. But I want to point out that you can still run an ANOVA. The ANOVA statement will still work when you're running this type of GE model. But if you look at what's produced here, the ANOVA is not based on the likelihood ratio statistic, because that's not valid because of the quasi-likelihood. Instead, the ANOVA is based on a walled statistic. And it will give you this table of p-values for each of your different variables in the model. And whereas the summary table produced previously gave sort of one p-value for each level of these 3-level variables. This will give you an overall p-value for both levels here. And finally, I'm going to also look at an autoregressive working correlation structure. And the AR1 is the option for autoregressive that comes with the GEGLM function, and that is an autoregressive correlation structure with lag 1, which is the most common AR structure. Visits in time here will be more correlated. And this type of correlation structure is only suitable for measurements made at equally spaced time points, which is true in our data because we have measurements made once a week at every week. But if you had time points not equally spaced, then you can't use this type of correlation structure. And again, that AR1 is specified by this last argument of the function. So under ideal conditions for the sandwich estimator, our estimates for the standard error should be robust to your choice of working correlation structure. And so how do we know that those assumptions are satisfied? And when I say robust, what I mean is that the estimates that you get for the standard errors, as well as the inference based on those estimates, should be relatively similar across different choices of your working correlation if the assumptions for the sandwich estimator are met. So it's good to check them anytime that you run on GEE. So the first condition is that the number of observations per subject is much less than the total number of subjects. In this case, we have 12 observations per subject and 72 total subjects. So this is definitely, the number of subjects is larger than the number of observations per subject, but I think ideally we would have an even greater gap between these. But at least that's sort of a reasonable assumption to make here. The second is that data is reasonably balanced across time and covariates. Well, here you can see that each of the different time points, we have an observation for every single subject except at the very last time point where we're missing observations for 3 subjects, which indicates that in general the data is reasonably balanced, but you do have a few missing observations at the last time point. And finally, we want to know that there are a similar number of observations per subject. And we can see here that all subjects have either 11 or 12 observations. So in general, that is satisfied. So ideal conditions would mean a larger sample size here, a larger number of subjects, but in general, the assumptions are reasonable in this case. Yeah, if these assumptions are not met, then you'd need to be careful about how you choose a correlation structure and really look at the estimates across models with different correlation structures because they could be quite different. So how do the estimates and standard errors compare across these 3 models with 3 different working correlation structures? You'll see those in the next slide, but generally speaking, the estimates are a little different for the AR1 structure than they are for the others. But you're drawing relatively the same conclusions across the models. And this code here is just extracting the coefficients and p-values from each of these different models and printing them out in a nice table. So this table shows the intercept and covariate terms, their estimates and their standard errors and p-values across the models with the 3 different correlation structures. And you can see for the intercept, they're very similar for exchangeable and for independent, and similar for AR1, a little higher. And you see that same trend across all of the other estimates where the independent and exchangeable have quite similar estimates and the AR1 is a little bit different. And then our standard errors have the same trend across all of the different betas that we have calculated. And you would also, looking at the p-values, you get the same you draw the same conclusions based on p-value for across all of the different working correlation structures. And this is good. That means that our inference is going to be relatively robust regardless of which correlation structure we choose. So how do we know which one to choose, though? We still have to pick one of the models with one of the correlation structures. And QIC can help with that. QIC is analogous to AIC, except it's developed for GEEs, which have the quasi-likelihood instead of the true likelihood. And here you can use this to compare models with the same mean structures but different working correlation structures. The QICs are given by this QIC function. They're the first number that is printed out, and you can see that QIC is lowest for the exchangeable model, so we would go with that one. So how do we interpret parameters in this model? Well, one of the nice things about GEEs is that the interpretations are really the same as the cross-sectional GLM model, with the added consideration that these effects are at the population level. So in this case, we have the same interpretation as linear regression. Here, beta 0 is the intercept, which is 15.098, and this is the expected weight at time 0 for pigs with no vitamin E and no copper in their diet. There's a subtle difference here when we're considering things at the population level. In a cross-sectional case, you might say that beta 0 is the expected weight for a pig at time 0, but here we would only say it's the expected weight at time 0 for pigs. We wouldn't say for a pig, because that assumes sort of a subject rather than a population level structure. Okay, so the beta for time is 6.94, and this is the expected increase in pig weight for each 1 week increase in time, controlling for vitamin E and copper. And I only have one of the betas here for the different doses, but this is a dummy variable comparing a dose of copper of 35 milligrams per kilogram to a dose of no copper. And we'd say that the expected difference in weight comparing pigs who received 35 milligrams per kilograms of copper to pigs who received no copper is negative 0.765, which is actually very small. We see basically almost no weight difference here based on copper dose.